Hello, um, welcome back. So, I'm doing this video in continuation with my previous video, which was design of steel structures hyphen bolted connection hyphen example 1. So, this is a similar problem. So, many of the things which we will be encountering in this particular problem I have already discussed in the previous problem, that is example 1, and hence uh, I will not be explaining everything in detail. For any clarification you are requested to go through the previous video uploaded. So let me get back to the question. Determine the safe load carrying capacity in tension of a lap joint connecting two plates of 16 mm and 12 mm thickness. So basically here once again it's a lap joint. The two plates are subjected to tension, and the thickness of the two plates are 16 mm and 12 mm. In our previous problem it was same thickness, whereas in this problem the thickness is different, 16 mm and 12 mm. The bolt threads are outside the shear plane. So which means in the previous problem we made an assumption that the threads are included in the shear plane, whereas in this problem it is very clearly indicated in the question itself that the bolt threads are outside the shear plane, that is threads are excluded from the shear plane. M16 bolts and Fe 410 grade steel is used. Okay, so we are also asked to find out the efficiency of the joint along with determining the safe load carrying capacity. Okay, so that is the question. So similar to the previous problem, sketch is also given. Okay, you cannot expect that the sketch will be provided in all the cases. Sometimes instead of providing the sketch they might have given you the number of bolts which are used to connect the two plates. Okay, so you will have to actually draw a sketch by yourself. So in this problem anyway, since the sketch is given, let us have a look at it. Yes, 16 mm and 12 mm plate lapped, and as you can see there is only one shear plane. Okay, so edge distance maintained is 30, the pitch is 80, again the edge distance is 30, so overall the lap distance is 140 mm. And finally again this edge distance is also 30, then gauge is 60, and the total width of the two plates are same, both are 120 mm plates. Okay, so let us start the problem by writing out what are the given information, what are the inferences we can make from that, and possibly what are the assumptions we would like to make before starting the problem. So yes, it is given that M60 bolts are used, which means as we already discussed in the previous problem from table 19, we can find out the diameter of the bolt hole, which in our case with a 2 mm tolerance will come around 18 mm. Then since mild steel or Fe 410 steel is used, the ultimate tensile strength of the plate is 410 Newton per mm square, and yield strength of the plate is 250 Newton per mm square. And since 4.6 grade bolt is used as indicated in the problem, okay, fine. So which means the bolt grade is not indicated in the problem. Fine. So in that case we'll have to make an assumption at this particular stage, okay, that the connection is a bearing type connection with 4.6 grade bolt. Okay, with that assumption we are considering that the ultimate strength of the bolt material is 400 Newton per mm square. Okay, once again let me reconfirm. the details of the bolt is not given, only the diameter is given, yes, you will have to assume that it is a bearing type connection and the bolt grade is 4.6 grade, and hence FUB is equal to 400 Newton per mm square. Partial safety factor gamma MP 1.25, gamma ML is again 1.25 and gamma M0 is 1.1. This is obtained from table 5. So as you can see, gamma MB you have two cases, site bolt or shop bolt, but anyway, as far as a bearing type connection is concerned, both conditions will have the same value of gamma MB, that is 1.25. So it is not important that we make an assumption whether it is a side bolt or a shop bolt, both will have the same value. And then let us discuss the limit states that are applicable. Similar to the previous problem, we have 4 limit states applicable, which are the shearing capacity of the bolt, the bearing capacity of the bolt or the plate, and then tension capacity of the plate, and then blow shear rupture of the plate. Okay, so let us begin with shear capacity of the bolts. Okay, so here the equation is FUB by root 3 into NN ANB plus NN NS ASB. So as we already discussed, there is only one shear plane, and in that shear plane the thread is excluded from the shear plane, which means NN becomes 0 and NS becomes 1. So ANS is equal to pi by 4 d square, where d is 16 and ANB is equal to 78% of ANS. So from this we get the value of VDSB as 37.1466 kilonewton, which means for all the 4 bolts together, the total capacity of the bolt corresponding to shear is 148.586 kilonewton. So next limit state is bearing capacity of the bolt. Here the equation is V and PB is equal to 2.5 into KB into D into T into FU. So maybe we will have to make a judgment at this particular point with regard to the minimum edge distance. Okay, so as we can see from the relevant clauses, we will have to find out the minimum edge distance which is required to be provided. Okay, so in any case, in any way, even if it is not provided in the sketch, for example, maybe they might be showing only the number of bolts, they may not give you the edge distance, the pitch, etc. So then you will have to calculate it. So similar to what we have discussed in the previous problem, you can find out the minimum edge distance required by assuming whether your edge of the plate is planed edge or sheared edge. So if it is a machine planed edge, the value minimum value required is 1.5 into D0. Okay, anyway, so here what they have done is they have calculated it with the help of D0, and as you can see, the equation used is 1.5 D0. Disregard 3 by 2, actually it is 1.5 D0. So as you can see, 30 mm is 27 mm is required, and we have provided 30 mm. Then minimum pitch required is 2.5 times D. Okay, so the required is 40 mm. So if you look at the pitch and the gauge, the minimum value is 60 mm, so which is more than 40 mm, hence we can go with that. Now we need to find out the value of KB. So KB need to be find out corresponding to the 4 equations, that is E by 3D0, P by 3D0 minus 0.25, FUB by FU, and the maximum value can be 1. So similar to what I have discussed, if you might observe in the previous problem, I have actually changed the value of P in the previous problem. So here also that change is applicable, because you will have to, when you take P, So generally we are actually considering the pitch. So here the pitch is 80 mm, and gauge is 60 mm. So instead of 60 over here, it was supposed to be 80. Anyway, it's not a big deal, because anyway the second condition will not be governing. Most of the cases the first condition will be governing, but if ever the second condition is governing, then you should be looking into this particular aspect also. And FUB by FU, normally normally in all the cases it will be an apparent value, and finally 1. So from these values you can observe that the minimum value is 0.555. so that is taken as the value of KB. Now yes, we need to substitute D. We know that D is 16 mm, and FU, we know that FU is 400 Newton per mm square. Now what is T? So T should be taken as the minimum thickness of both the plates, because we already discussed the meaning of T. So it is the cumulative sum of the thicknesses undergoing bearing stress, or withstanding bearing stress in the same direction. So when there are two thicknesses available, you should be taking the lowest among that. So in this case we will get the value of VDPB as 87.38 kilonewton, that is for 1 bolt. So for 4 bolts the value is 4 into 87.38, that is 349.517 kilonewton. Now similar to the previous problem, you can, at this particular point, it is possible for you to tell what is the bolt value of the bolt used in the problem. So it is the lesser of bearing capacity and shear capacity, and bearing capacity we already calculated. For 1 bolt it is 37.1466, okay, and hence that is a bolt value, because bearing capacity is much greater than that. So bolt value of the bolt used in this particular problem is 37.1466 kilonewton. Fine, let us get into the second limit, or the next limit state, which is the design strength of the plate, where we will be actually evaluating the tensile strength of the plate. Okay, so which is limit state corresponding to the plate acting as a tension member. Okay, so as you can see, since the bolts are arranged symmetrically, so you have 2 rows of bolts and equal number of bolts are provided in 2 rows in a straight line. So possibly the failure pattern or the failure path will be as shown here, a straight line. Okay, so and that too we should be actually calculating the failure path, okay, for the plate with minimum thickness. Okay, because that will be governing. Definitely the plate with the minimum thickness will be governing our design. So we'll be taking the values corresponding to 12 mm thick plate. So TDN need to be calculated. It is 0.9 AN FU by gamma L. So as we discussed in the previous problem, the second part of the equation for AN, the second part corresponds to any inclined failure path available. So in our case there is no inclined failure path, so this becomes 0, and we need to substitute the value of B, N and D0. Okay, finally we got the value of AN as 1008 millimeter square. So finally TDN is obtained as 297.5616 kilonewton. So far so good. Next limit state applicable is design strength due to block shear or block shear rupture strength. So this is once again the property of the plate acting as a tension member. The block shear rupture, as we already discussed, need to be evaluated for 2 different cases. Okay, so here once again we need to calculate AVG, AVN, ATG and ATN. So here we don't have much trouble, because much similar to what is indicated in the IS code under the section corresponding to the block shear rupture, the plates will be actually undergoing the block shear rupture in a pattern which is indicated here. As you can see, the failure path will be like this: 2 horizontal lines which corresponds to the shear failure path, and one vertical line which corresponds to the tension failure path, and this hashed portion will be the block which will be getting separated from the remaining of the plate. Okay, so there is no much complexity in the calculation, so it is much straightforward. So yes, maybe as you can see in the case of AVN AVG, it's straightforward. AVN, once again let me state that 1 ton is the total distance, that is of one shear failure path, 80 plus 30, which becomes 1 ton. And how many bolts are included in this failure path? As you can see, the distance is measured from the center of the bolt hole here to the edge of the plate, so which means 1 bolt hole plus half bolt hole. So maybe I didn't explain this particular thing in the previous problem, considering that you are aware of that, but still if you require any clarification, let me reinstate that. Yes, this failure path, if you look at it, starts from the edge to the center of this bolt row. So when you look at the shear failure path here, 1.5 bolt hole reductions need to be taken as far as AVN calculation is concerned. Okay, finally it should be multiplied by 12 mm, because we are actually considering the failure of 12 mm plate, which is the lesser among the plate with lesser thickness among the both. And similarly, when it comes to ATG corresponds to the gross area of the tension failure path, okay, which is the distance between the center of this bolt to center of this bolt, and it is straightforward. Then ATN, as we can see, half bolt hole reduction is available here and half bolt hole reduction available here, so that is why they have taken 0.5 into 2, half here and half here, 0.5 into 2, so total 1 bolt hole reduction as far as ATN calculation is concerned. So from that we can actually calculate TDB, okay, which is 495.191 kilonewton, and in second condition it is 503.14 kilonewton. Among these two, the lesser value is 495.191 kilonewton, which will be considered as the block shear rupture strength of this particular plate. So as we can see, other than what we have witnessed in the previous problem, there was a bolt which didn't failed, okay, which was actually intact in the portion which was separated as a block, whereas in this problem there is no such bolt. Almost all the bolts or the bolt locations are witnessing a failure path. So I mean, you don't have to add any bolt strength or bolt value along with the calculated values of TDB. So the block shear rupture strength becomes 495.191. Now we have to consider all the 4 limit states, and we'll have to take the lesser among all the 4 limit states as the strength of the joint. So as we can see, most probably our shear strength calculation, which corresponds to 148.586, okay, is going to be the most critical among all the calculations that we have done. Yes, invariably the ultimate strength of the joint is 148.586 kilonewton, which corresponds to the shear capacity of the 4 bolts. Okay, finally let us conclude this problem by calculating the efficiency. As I have already discussed, efficiency of the joint is actually a percentage which is expressed in terms of strength of the solid plate. So strength of the joint divided by strength of solid plate multiplied by 100, okay, will give you the efficiency, and in our case we get the efficiency as 45.401 percentage. So here the strength of the solid plate once again is calculated corresponding to the design strength of the plate, okay, considering the yielding of gross cross section, which is again a property of the plate acting as a tension member, and is taken as per clause 6.1. So let us conclude this problem by stating the answers. The ultimate strength of the joint is 148.586 kilonewton, and the efficiency of the joint is 45.401 percentage.